Welcome. We will continue our discussion of the statistical thermodynamics of an ideal gas comprised of diatomic molecules, and in today's lecture we are going to talk about the homonuclear diatomic ideal gas. So, as discussed before, the homonuclear diatomic system is comprised of molecules like this, where both the atoms forming the molecules are of the same type. So, examples are hydrogen, deuterium, oxygen, nitrogen and so on, and other halogens. In this case, before we go into the discussion of how to work out the statistical thermodynamics of a system like this, it is very important to understand the difference between this case from the heteronuclear system. In this case, simply because the two nuclei or the two atoms constituting the molecule are identical, there are additional demands of symmetry from in this system. So, the first thing that we should note down that the total wave function psi of the molecule must possess rather specific symmetry properties under the operation where we interchange the two identical nuclei. Now, we are going to have a very detailed look at these two terms. First, what I mean by this interchange of the two identical nuclei, and second, what kind of specific symmetry properties am I talking about. If I want to just show you, highlight the kind of symmetry property I am talking about here, we would like to have this overall total wave function psi symmetric with respect to interchange of two identical nuclei for integral nuclear spin. But if it so happens that the nuclear spin is half integral, in that case psi must be antisymmetric with respect to interchange of the two nuclei. And therefore, let us take up these little different concepts of interchanging of the two identical nuclei and what effect it has on the overall wave function as well as the single particle partition function. And then we consider how to assign what is the specific symmetry requirement for different nuclei having integral or half integral spins. So, the first thing that we would talk about is something that has been shown here in this approximate diagram. For the sake of simplicity, I will confine my discussion here in a two-dimensional space. So, this is the direction of my x axis and this is the direction of my y axis. This is something that represents the nuclei and the electron cloud in the diatomic molecule, which is given here. Now, the red portion corresponds to the nuclei and the yellow portion corresponds to the electron cloud surrounding it. So, this is obviously a rather approximate representation of the diatomic molecule. And now, if I carry out an interchange of the identical nuclei in a diatomic molecule, what I will do is I will do this in two steps. So, the first step is we will invert all the constituent particles of the molecule including the electrons and the nuclei through the origin. So, in this picture, where is the origin? This point is my origin. So, if I want to invert this body or this point through this origin, I should appear here. And therefore, what I am trying to say is this is an inverted image of this and vice versa. Now, as you see that I have this particle 1 and this particle 2, and here for the sake of our understanding, I have colored the nucleus of the particle 1 or the as red and the electronic cloud as yellow. Here for this particle 2, what I have done is I have used as the center black and as the electron density green. Now, in the first step, if this is my starting configuration, I have 1 here, 2 here, and I would like to invert all the constituent particles through the origin, and this would definitely result into something like this. So, obviously, this will go to this position as we see in this picture, and this will come to this position as we see in this picture. Now, after this, we would have a second step of inverting the electrons back through the origin, and this is what we will get. So, now if I compare these two pictures, what I get is through this interchange of these nuclei, what I have obtained is starting from this structure, simplified, highly simplified structure, I have landed up in a structure like this, where as you see that it is the same electron density at these two positions, it is the same electron density at these two positions, but only the nuclear positions have been exchanged. So, this is a pictorial representation of what I mean by interchange of the identical nuclei in a diatomic molecule, which means that if to start with I had a configuration like this, I am going to go to a configuration like that as a result of the interchange of the identical nuclei. Now, under such condition, under such operation, this inversion, we would like to talk about what happens in 3 dimensions. Now, obviously, in 3 dimensions, you can work in the Cartesian coordinates. In the case of the Cartesian coordinates, what you will find is that inversion through the origin results in transformation of the coordinate x, y, z into minus x, minus y and minus z. In many cases in quantum mechanics, the exactly solvable models involve solution of the Schrodinger equation using the spherical polar coordinates, just as in the case of hydrogen atom. So, in that case, instead of x, y and z, one uses the 3 coordinates for each point r, theta and phi. Now, inversion through the origin results in the following conversion. So, let us have a pictorial look at what these conversions mean and then proceed further. So, this is a representation of the Cartesian coordinates in the 3-dimensional space. This is the direction of my x axis, this is the direction of my y axis and this is the direction of my z axis. So, this plane is nothing but the x y plane. Now, if I have one point here which when inverted through the origin will land up here. So, if this point is above the x y plane towards the direction of positive z, through by inversion through the origin it will land up below the x y plane and near and in the direction of the negative part of the z axis. Now, if I introduce here the spherical polar coordinates and define them as x is r sin theta cos phi, y is r sin theta sin phi and z is r cos theta, where I have taken the same point having the coordinates x, y, z and I define its radial distance from the origin as r. Okay. So, this distance between this point and this point is my radial distance r. Now, what is theta? If I take this straight line and find out the angle made by it with the positive side of the z axis, that is given by theta. So, this is where it appears in the relationship between x, y, z and r theta phi, and there is another coordinate which gives you the, if you take a projection of this vector on the x y plane and then you find out the angle made by this particular line, which is the projection of this r vector on the x y plane, that is phi, and phi also appears in the relationship between the two sets of coordinate systems, but z is independent of phi. Now, with this definition we understand that if we replace now x by minus x, y by minus y and z by minus z, there are only certain relationships which are allowed for the new values of r, theta prime and phi prime, and these values are given in terms of the changed numbers that I have noted here. Obviously, inversion preserves the distance from the origin and therefore, r remains unaltered. Then if you think about theta, instead of being here, now for this theta is going to be this distance and the angle it makes with the positive side of the z axis. So, that would be pi minus theta, and similarly you can very easily show that phi will be replaced by phi plus pi. So, under such condition, let us now try to think about what happens when I carry out this inversion, or which means that a change of the coordinate system such that x goes from goes to minus x, y goes to minus y and z goes to minus z, or some equivalent coordinate transformation as far as the spherical polar coordinates are concerned. Now, we have already noted that my total wave function is a product of something like psi prime and a psi nuclear. Okay. Now, psi nuclear is the nuclear wave function and it is associated with the solution of the Schrodinger equation for the nuclear energy eigenstates. Now, what is psi prime? In our discussion of the heteronuclear diatomic molecule, we actually looked at the different dependencies of this psi prime on the translational degree of freedom and electronic degrees of freedom, then vibrational and rotational degrees of freedom. So, under the approximation of rigid rotor simple harmonic oscillator, I can write down that psi prime is a product of these individual wave functions, psi trans corresponding to the translational motion of the center of mass of the molecule on the whole, psi electronic is corresponding to the solution of the electronic energy eigenstates corresponding to the molecule that we have at hand. Psi vibration corresponds to the vibrational fine structure associated with this diatomic molecule, and finally, psi rot corresponds to the rotation of the molecule like a rigid rotor. So, once we have this in hand, then the question is, when I do the inversion or carry out some kind of a coordinate transformation, then what would be the result of such transformation on the different parts of psi prime? So, let us investigate the different parts of psi prime to start with, and this is what we get. Now, psi trans, the first term, psi trans, it depends only on the center of mass coordinates, okay? And therefore, when you carry out the inversion of the coordinates, the center of mass coordinate actually remains unchanged, and therefore, I would say that through this interchange of identical nuclei, psi trans is going to remain unchanged. So, psi trans is symmetric with respect to interchange of identical nuclei in this diatomic molecule. Similarly, if I look at psi electronic, what I find is that in most of the cases, in most of the diatomic molecules, in general, the ground electronic state is supposed to be symmetric with respect to inversion through the origin. Okay? As a result, I would say that under this interchange of identical nuclei, in this inversion process, that will also leave psi electronic in most cases unchanged. Therefore, this is symmetric with respect to this operation. Now, think about psi vibration. In the case of psi vibration, this depends on displacement from the equilibrium bond length. So, this is some kind of an internal displacement which does not depend on where what has happened, whether you are looking at it in the after inversion or before inversion. So, once again these displacement within the molecule will remain unchanged when I interchange the two nuclei. As a result, all the three wave functions that are shown here, psi trans, psi electronic and psi vibration, will remain unchanged, and these are symmetric with respect to interchange of identical nuclei in the diatomic molecule. But of course, I have not talked about psi rot. So, let us go and see, have a look at a closer look at what happens to psi rot, and if at all it has any it shows any effect as a result of this interchange of identical nuclei. So, the next thing that I do here is focus on this. Now, under the rigid rotor harmonic oscillator approximation, I understand that psi rot is nothing but the rigid rotor wave function, and this has the same property as the angular part of the wave function for hydrogen atoms. Now, this particular observation tells us that I can use the properties of hydrogen bond orbital hydrogen atom orbitals to understand the symmetry symmetry properties of the wave functions for a rigid rotor case. So, this is the first case. So, what happens, psi rot, different rotational wave functions are associated with different rotational quantum numbers j. We have seen that these values of j, they can vary from 0, then take up values like 1, 2, 3 up to infinity. Now, let me take this first case where j is equal to 0. Now, when j is equal to 0, the symmetry properties of the wave function is like the 1s orbital of the hydrogen atom. And in this case, what we have done is, we have shown you what happens to the s orbital when this is the direction of x axis, this is the direction of positive y axis, and this is the direction of z axis. Now, if I take a point here and I invert it through the origin, which is at the center of the orbital, then will there be any change in this wave function in the sign? The answer is no. And therefore, the result of inversion is that it will leave the wave function of j equal to 0 unchanged, and therefore, we conclude that whenever I am talking about the j equal to 0 wave function of a rigid rotor, I must be having a symmetric psi rot. Now, let me also look at the other cases, like when j is equal to 1. Now, when j is equal to 1, this is the case where I have the rigid rotor wave function displaying symmetry properties exactly like the p-like. Okay. So, now if it is p-like, then here we have shown the dependence of the orientational dependence of the different solutions which are associated with j equal to 1. There are 3 solutions, and as you see, the point is that here, if I carry out an inversion through the origin, which are here at the nodal points of the p orbitals, I know that the wave function changes sign as it goes from x to minus x, or plus y to minus y, or plus z to minus z, and therefore, I would say that for j equal to 1, the wave function undergoes a change in shows a change in the way it is projected across the center, and here the associated psi rot must be antisymmetric. Similarly, if I go ahead and look at what happens to j equal to 2, once again these are d-like properties, and therefore, the wave function is shown to be symmetric with respect to the interchange of identical nuclei. Now, with all these results in hand, then what we can do is we can say the following. I am looking at this kind of a process where I am going to look at the interchange of the identical nuclei, and I am going to do this through an inversion, by an inversion through the origin, which is the midpoint shown over here. Now, the symmetry property of overall psi will now depend on the symmetry property of psi prime and psi nuclear. I will come to the case of psi nuclear a little later, but let me first look at the symmetry properties of psi prime. Now, psi prime depends on these 4 factors, of which this and this, these are clearly symmetric with respect to the interchange of the nuclei. So, we are left with these 2 terms, psi electronic and psi rotational. Now, as I have already mentioned that in most of the cases, psi electronic is a symmetric ground electronic state, which is which remains unchanged with respect to inversion through the center. Therefore, we find that the symmetry requirement on psi prime is imposed entirely by psi dot, and then we can say that psi prime is symmetric if you are looking at rotational energy states associated with even values of the rotational quantum number. Now, psi prime will be antisymmetric with respect to interchange of the identical nuclei in a diatomic molecule if we are looking at the rotational energy states associated with odd values of j. Okay. So, this is the most common scenario as far as the behavior of psi prime is concerned in response to interchange of identical nuclei in this diatomic molecule. Obviously, then the next part is to consider psi nuclear. Now, when I consider psi nuclear, we will go very slowly here because there are several concepts which are associated in this treatment, where we find that it is not enough to talk in terms of the electronic energy states, overall translation of the molecule, as well as the electronic, nuclear, as well as the translation energy of the molecules, but we have to very closely look at the consequence of having 2 identical nuclei which must preserve certain symmetry requirement depending on what the nuclear spin is. Now, going back, let me take an example. Let me take the simple example of hydrogen molecule. In the hydrogen molecule, there are 2 nuclei, the 2 nuclei corresponding to the 2 hydrogen atoms. Now, if I ask you the question, what is the nuclear spin on each of these hydrogen atoms? You would say that from our initial knowledge about atomic structure, I know that each hydrogen atom nucleus is associated with a nuclear spin of half, and then I would say that then there will be nuclear spin eigenfunctions alpha and beta. There will be 2 such nuclear spin eigenfunctions, and they are obtained by saying that, well, if you have a nuclear spin I, how many nuclear spin eigenfunctions do you expect? 2I plus 1. Now, when I have I is equal to half, I understand that 2I plus 1 is equal to 2 into half plus 1, that is equal to 1 plus 1, that is equal to 2. Okay. So, one of these nuclear spin states is given, the wave function is given the symbol alpha, and the other one is given the symbol beta. Okay. Now, I have 2 such nuclei. So, this is for 1 hydrogen atom nucleus, and I have 2 such hydrogen atom nuclei. Okay. Then the question is, if I can assume that the nuclear states of each hydrogen atom are occupied independent of each other, then the psi nuclear will involve how many nuclear spin functions? It will involve 4 nuclear spin functions, and these are alpha alpha, alpha beta, then beta beta, 1 by root 2 alpha beta plus beta alpha, and 1 by root 2 alpha beta minus beta alpha. So, this means that both the nuclei are existing in the state such that it has spin wave function alpha and this has spin wave function beta. Now, there is the second possibility is that both of them are existing in the state corresponding to beta spin wave function for the nucleus 1 and beta spin function for the nucleus 2. And it may so happen that one of them have alpha spin wave function, the other one has beta spin wave function. And quantum mechanics requires that under such condition you take a linear combination of these two, and these are the probable combinations that are allowed by this in this particular case. So, these 4 nuclear spin wave functions are alpha alpha, beta alpha, then a combination of alpha beta and beta alpha. Okay. Out of these, as you see that I have clubbed these 3 together and I have labeled the 4th one separately. Do you understand why? That is because if you closely look into the symmetry properties of each of these nuclear spin wave functions, you will find that these 3 wave functions are symmetric with respect to interchange of the identical nuclei, and here these 2 are antisymmetric with respect to interchange of the 2 identical nuclei. Now, this is some concept that we are going to use further, where we use it to understand what are the symmetry properties of psi nuclear would be. In the next lecture, we shall once again start from this particular example and discuss the general symmetry requirement of psi nuclear and then the overall symmetry requirement of psi in a homonuclear diatomic molecule. Thank you.